Neurons transmit chemical signals across synapses, like the one shown in this electron micrograph. We can identify the dendrite of the receiving or postsynaptic cell, as well as two presynaptic nerve terminals loaded with synaptic vesicles. Note the narrow cleft separating the pre- and postsynaptic cells. The synapse converts the electrical signal of the action potential in the presynaptic cell into a chemical signal. When an action potential reaches a nerve terminal, it opens voltage-gated calcium channels in the plasma membrane, allowing calcium ions to flow into the active zone of the presynaptic terminal. At the active zone, synaptic vesicles are docked via the binding of V snares on the synaptic vesicle membrane with T snares on the presynaptic plasma membrane, which forms a partially assembled snare complex. Calcium ions bind with synaptotagmin located on the vesicle membrane. This binding triggers the full assembly of the snare complex. The full assembly of the snare complex generates a force to bring the synaptic vesicle membrane and the presynaptic plasma membrane next to each other. They fuse and thereby release the neurotransmitter content of the synaptic vesicle into the synaptic cleft. When the released neurotransmitters diffuse across the synaptic cleft, they bind to and open the transmitter-gated ion channels on the plasma membrane of the postsynaptic cell. An excitatory neurotransmitter, such as glutamate in the vertebrate central nervous system, causes a net influx of cations. This depolarizes the plasma membrane of the postsynaptic cell and contributes to action potential firing of the postsynaptic neuron. Thus, the neurotransmitter's chemical signal is converted back into an electrical signal. The neurotransmitter is quickly removed from the synaptic cleft, either by enzymes that destroy it or by reuptake into the nerve terminals or neighboring glial cells.